Hello, Stat students. Today we will do 6.3b notes describing a binomial distribution with center and spread. We describe the probability distribution of a binomial random variable just like any other distribution. We will look at the shape, center, spread. We can always address outliers as well if we see any, but these are like the main things. You always want to address all four. Consider the probability distribution of X, where X equals the number of children with type O blood in a family with 5 children. Below you see a probability distribution. So you have the row indicating the number of children 0 to 5 and their probabilities on the bottom row. So what we could do is we could put this in list 1 and we can put the probabilities in list 2 and we can do a one variable stats where L2 is your frequency, and that'll give us our mean and standard deviation. When we do that, we get the mean to be 1.25, but it can also be found another way if we didn't use a calculator. Since each child has a 0.25 chance, so that's 1/4 of inheriting type O blood, we'd expect 1/4 of the 5 children to have this type of blood. So the mean of X is equal to 1/4 of 5, which is 5/4, which is also 1.25. This method can be used to find the mean of any binomial random variable with parameters n and p. Before we go any further, to the right, let's go ahead and just sketch this so we can just describe what the probability distribution looks like, the binomial distribution looks like. So with when X is 0, the probability is 0.2373. So just something like this. We're just going to do a rough sketch. Okay, for 1, it would be 0.3955. For 2, it would be 0.263 something. For 3, 0.08. So right about here maybe. For 4, 0.0147. And 5 is barely the line there. So it's right skewed. Makes sense that the mean is somewhere right here. Well, the first one, I'm just shading this in. And that's pretty much all that we can talk about other than those are the main things. I just wanted to show you what it looks like, that it looks like any other distribution. As far as the standard deviation mean formulas go, if a count X has the binomial distribution with number of trials n and probability of success p, then the mean and standard deviation of X are, so the mean of X is equal to n, the number of trials, times the probability of success. Okay. And that works for any binomial distribution. Both of these are on your formula sheet. And the new formula sheet actually says it's for a binomial distribution. It used to not say that, but it does now. So that's great. Okay, for the standard deviation, that particular formula is the square root. I don't know why that did that. It'd be the number of trials times the probability of success times the probability of failure. Well, if P is your success, 1 minus P is your failure. So success, failure. These formulas work only for binomial distributions. They can't be used for other distributions. Here's an example. To introduce her class to binomial distributions, Mrs. Desai gives a 10-item multiple choice quiz. The catch is students must simply guess an answer, A through E, for each question. Mrs. Desai uses her computer's random number generator to produce the answer key so that each possible answer has an equal chance to be chosen. Patty is one of the students in this class. Let X equal the number of Patty's correct guesses. Find the mean of X. Interpret this value in context. So the mean of X is equal to n times the probability of success. So n, in this case, the number of trials would be 10, or the number of questions, items, and your probability of success for each one is 0.20 or 1/5. And the reason why it's 1/5 is because A through E for your multiple choice is a total of 5 options. And so that would equal 2. So, and then we have to interpret it. So after taking the quiz many times, many times, we'll just say many times here, we know it. On average, Patty would Patty would guess 2 questions correctly, or we would expect. It's probably better since it's expected. We would expect Patty to guess 2 questions correctly. Find the standard deviation of X. Interpret this value in context. So the standard deviation of X is equal to the square root of n times p. So 10 times the probability of success, which is 1/5, times the probability of failure, which is the remaining. So if 1/5 is a success, 4/5 is your failure, because 1/5 and 4/5 always add up to 1. And so when you do the math, you end up getting the standard deviation. So inside the square root, you are going to have 40 over 25. And that will give you a standard deviation of 1.26. Interpreting standard deviation, on average, it is the deviation from the mean. The number of questions Patty will get correct, or guess correct, right, will vary from the mean of 2 by about 1.26. There you go. So the interpretations are a big key thing for students. Lastly, on this question, what's the probability that the number of Patty's guesses is more than 2 standard deviations above the mean? So not below, but above. So the mean is 2. So if you add 1 standard deviation to that, that would be 3.26. Now add 3.26 plus 1.26, and that'll give you 2 standard deviations above the mean. So this is what it would look like. The probability that Patty's score is greater than 2 standard deviations above the mean. So all you want to do is take the mean, which is 2, plus multiply 2 times 1.6. So that's 2 standard deviations above the mean. And that'll give you the probability. So that ends up being 4.52. So X is greater than 4.52. So we have to think about this for a second. You're not going to get 4.52 questions right. So she can get 4 questions. Oops. Or 5 questions correct here. And so to do that, in terms of probability, you could do probability that x is greater than or equal to 5, because there 5 is included, 5 and above. Or you can do the probability that x is greater than 4. That takes care of the 4.52 in there. And so in order to do that, we would do a binomial CDF because we have a range of probabilities. And so we're not going to use the point distribution. We wouldn't use binomial PDF. So 1 minus the probability of x is less than or equal to 4, which is 1 minus binomial CDF. Oops. And our prompts are the number of trials is 10. The probability of success is 1/5. And our value here, because x is less than or equal to 4, would be a 4. And that would give us 0.0328. So the probability of Patty's guesses would be about 3.28%. Now, binomial CDF is really difficult at times because we don't know, our calculator only does less than or equal to. So there would be a better technique to use, and that is going to be our next topic of the day. And that is the binomial distribution in terms of normal probabilities. Actually, that's not yet. Instead of normal approximation. So that's not yet though. So the binomial distributions are important statistics when we want to make inferences about the proportion P of successes in a population. We always want to go back and see if we can infer to our population. That's a goal of statistics. Consider 10% of CDs have defective copy protection schemes that can harm computers. A music distributor inspects a simple random sample of 10 CDs from a shipment of 10,000. Let X equal the number of defective CDs. What is P? What is the probability that X equals 0, so that there are 0 defective CDs? Note, this is not quite a binomial setting. And why is it not a binomial setting? If you go through your bins, you would know that this is not an independent situation because we are not replacing anything back. So this is sampling without replacement. Ten CDs are examined, but they're not put back. So this is not a binomial setting. Therefore, you cannot use your binomial probabilities. So if you actually did the probability, here's how you would do it. If you know that 10% are defective, out of 10,000, that would be 1,000 that's defective. Therefore, 9,000, so 9,000 are not defective. So 9,000 over 10,000 would not be defective. Now you're going to start that's the first one that you'd look at. Then the second one, you'd have one less. So you have 9,999 CDs and one less in the numerator, 8,899 would not be defective. You do that all the way up until you get 10 CDs, and your 10th CD is your 8,991. So that from 9,000 to 8,991, that's 10 CDs. So you do the calculations, you multiply all the numbers, and you get 0.3485 as your actual probability because you can't use the binomial probability. However, using the binomial distribution, say we said it was okay that it met the 4 criteria of a binomial setting, even though we know it doesn't. Um, to find x equals 0, the number of defective CDs, you would do your binomial coefficient, which is right here. So 10, choose 0. And then our probability of success would be 0.10 to the 0 power, and then 0.90 to the 10th power. And that'll give you a probability of 0.3487. So take a look at this and take a look at the 0.3485. They're pretty close. So in practice, the binomial distribution gives a good approximation as long as we don't sample more than, and this is the key thing here, 10% of the population. This is known as the 10% rule, and it is so big in the second semester. So that's sampling without replacement. When we can't replace and we do sampling that way, how can we go about calculating a probability? We would use the 10% rule. When taking a simple random sample of size n, so lowercase n is like your sample, from a population of size n, capital N is the size of the population. We can use a binomial distribution to model the count of successes in the sample as long as the following is met. So the sample size, so lowercase n, is less than or equal to 10% of the population. So multiply the population times 0.10, and if n is less than or equal to that, that's okay. You could write this another way. If you're talking about the population would have to be greater than or equal to 10 times the sample. Whichever way, it means the same thing. So basically, right here, we can ignore I can say this is known as the independence rule. So we can ignore independence as long as the sample is 10% or less of the population. And that's why I wanted to show you the CD one and see how close those probabilities were. They're close enough. And then here below you have 3 pictures, and I just wanted to show you in each of those the probability is identical. It's probably 0.8, but the n, your sample size, gets larger. You start at 10, where this is a little it's left skewed. But then when you get to the center, when n equals 20, it's starting to look more normal looking. And then when you look at when n equals 50, it looks quite normal looking. It would be what we would call approximately normal. You never say it's completely normal. You're always going to say it's approximately normal. And when we have normal looking distributions, we can use our normal CDF, and we don't have to worry about subtracting, like less than or equal to, or subtracting from 1 or whatever. So it's easier when we get to use the normal probability. So normal approximations for binomial distributions. Suppose X has the binomial distribution with n trials and success probability of p. When n is large, the distribution of X is approximately normal with mean and standard deviation. So the mean is n times p, and the standard deviation, I don't know why it gets so crooked, n times p times 1 minus p. Take the square root of that, and remember that's on your formula sheet. As a rule of thumb, we will use the normal approximation when n is so large that this is the normal condition. n times the probability of success is greater than or equal to 10, and n times the probability of failure is also greater than or equal to 10. So both of them have to be met in order for you to be able to use your normal CDF. So this is super duper important. When both of those are met, you can use the normal CDF, and then you would put your lower bound, upper bound, your mean, which in this case would be n times p, and then your standard deviation, which would be n times the square root of n times p times 1 minus p, right? And then you would just enter those in your calculator. Let's do 2 sample problems. Sample surveys show that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that, quote, I like buying new clothes, but shopping is often frustrating and time consuming. Suppose that exactly 60%, 0.60, of all adult U.S. residents would say agree if asked the same question. Let X equal the number in the sample who agree. Estimate the probability that 1,520 or more of the sample agree. So first we're going to verify that X is approximately a binomial random variable. So we're going to check the conditions of a binomial setting. B, the success is whether they agree. Failure is don't agree. Well, we're not going to replace. There's no replacement in this particular problem. When you're dealing with people, you don't replace back. However, so no replacement. But remember, we're going to see if it meets the independence rule. Because the population of U.S. adults is greater than, and so what you would do is you would take the sample size, so it's 2,500 is your sample size, times the probability of success, I don't know what I was thinking. So times 10, so because the thing is you multiply, and that would, by 10, and that would give you the population, or capital N, to be 25,000. And so it's reasonable to assume that there are at least 25,000 adults in the U.S. And why the U.S.? Because it says of all U.S. residents. So that meets the 10% rule. And therefore, it's okay to check the independence condition. For n is the number of trials. So in this case, it is our sample size. So n is 2,500. And the probability of selecting an adult who agrees is 0.60. It's a probability of success. So it meets the binomial setting. Check the conditions for using a normal approximation. So we have to show this. We can't just go jump to normal CDF. You have to show that it meets the conditions, meets the normal condition. So since n times p, which is 2,500 is our sample size, a probability of success is 0.60. If you multiply those two, you get 1,500, which is greater than or equal to 10. And both of them, and you can't just show that they meet it, you need to show the actual values. And I tell students this all the time, and they might miss it the first time, but then they never make the mistake of not showing it. So that's 2,500 is your sample size, times the probability of failure. Well, success was 0.60, so failure is 0.40. When you multiply those two, you get 1,000. And they're both at least 10 or greater. And that's meeting, if you meet then you meet the normal conditions. So now we can calculate the probability that X is greater than or equal to 1520 because it says find the probability that 1520 or more of the sample agree. So here we can use a normal CDF. So you must show this. Our lower bound is going to be 1520. Our upper bound is going to be some large number. You could put 1,000,000 if you want to. It doesn't matter, but just something really bigger than 1520. And you don't want to pick something like 1600. And then our mean, so we need to calculate our mean. So the mean is 1500. We don't need to calculate it. It's right above. N times P is your mean. But your standard deviation, you have to, because you have to take the square root. So I'll do the standard deviation out here. So the standard deviation is 2,500 times 0.60 times 0.40. Multiply all that and take the square root of it, and you're going to get about 24.49489,743. Use as many decimals as you can. It'll just give you a really accurate probability. So your standard deviation is 24.494897, but significant digits don't matter in this class. So you're not going to get docked no matter whatever decimal places you use. When you put that in your calculator, you will get a probability of 0.2071. So there's a 20.71% chance that more than 1,520 people will agree. So make sure you know how to interpret that answer. What is it asking? What is it saying? They will agree with that statement. That 60% would say they liked buying new clothes, but shopping is often frustrating and time-consuming. All right, and our last example. In a survey of 506 teenagers ages 14 through 18, so 506 is going to be our N, it's going to be our sample size. So always circle or highlight stuff that's important. Subjects were asked a variety of questions about personal finance. One question asked teens if they had a debit card. Suppose that exactly 10% of teens ages 14 to 18 have debit cards. Let X equal the number of teens in a random sample of size 506 that have a debit card. Show that the distribution of X is approximately binomial. So here we're going to do everything on our own. Oops. Sorry about that. Okay, so for B, success is having a debit card. Failure is no debit card. Independence, well, you are not going to replace, but so therefore you have to show that's going to meet the 10% condition. So we will assume, always state it like that, assume that there are more than, take your sample size, which is 506, and multiply by 10. So there are more than 5,060 teens ages 14 through 18, and that is a valid assumption. We know that's the case. N is our number of trials. So N is, or sample size, sorry, it's 506. So I say 506, but I put 560. And our probability of success is 0.10. Check the conditions for using a normal approximation in this setting. And the whole reason is so we don't have to mess with the 1 minus the probability x is greater than or equal to a number. It's just so much easier to do it this way. So for the normal conditions, you want to show that n times p is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. So the sample size is 506. The probability of success is 0.10. And you don't just put in numbers, nor do you just skip and say, put a check mark right next to the formula and say it meets. Verify with the numbers. So this is 50.6 is greater than or equal to 10. Right? There we have 506 times the failure, which is 0.90. When I multiplied those two together, I got 455.4, which is also indeed greater than or equal to 10. So the normal condition has been met. Now that the normal condition has been met, and we know it's a binomial distribution, use a normal distribution to estimate the probability that 40 or fewer teens in the sample have debit cards. So we're going to use normal CDF. Here, students get the numbers mixed up. So going back and actually sketching something like this, I'll show you. Oh, that's not very good looking, but I'm just going to show you what it should look like. So we know the mean is 50.6, so it's right here. We don't know the standard deviation, nor do we care for this, for what I'm showing you. You want 40 or fewer. So let's just, because we don't know the standard deviation, but we know 40 is to the left, so we can just say this is 40. We want this probability right here. So notice your upper bound will be 40, and your lower bound could be negative 1,000, or you can even pick 0. Just something that's less than that, depending on what your standard deviation is. So let's go ahead and figure out what our standard deviation is going to be. But our lower bound, so let's go ahead and do that. So over here, I'm going to calculate my, we don't need to calculate our mean because n times p, which is 50.6, was our mean. But our standard deviation is equal to n times p times failure. So 1 minus p. You do all that math, you end up getting 6.7483333128. And so your lower bound, so that's our standard deviation. So you want to subtract. So I was off quite a, well, I mean, I wasn't off because I never labeled my points or my tick marks over there in my distribution. So 50.6 minus 6.74, so 43 point something. So you want to pick, you could pick 0 and get away with that as your lower bound. So 0 is your lower bound. Your upper bound is 40. Your mean is 50.6. And your standard deviation is that 6.74833128. Put that in your calculator, and it will calculate your probability as 0.0581. So there is a 5.81% chance that 40 or fewer teens ages 14 through 18 have a debit card. And those are your notes for 6.3b. Have a great day, stat students.